My name is Chandler Carruth. I work at Google, where I lead kind of our internal programming languages efforts. I'm also one of the 3 Carbon leads, and I'm here to talk a little bit today. I have a kind of a strange presentation for me today. Usually I like to have like a message or a lesson, or I'm going to teach something really important. This is a little bit more of story time. And this is probably as esoteric of story time as you're ever going to get from me. This is programming language nerdery at its finest. I hope that's your cup of tea. If it's not, I will not be offended. If you're just like, this is too far down the rabbit hole, I'm out of here. But I also have a ton of content, so I'm going to go kind of fast. If you are confused, please raise your hand, let me know, and I'll try and explain. If you just have like deeper questions, please hang on to those, and we'll see if we have time at the end. So with that, I'm going to kick everything off. So it's been a couple of years. We were actually here 2 years ago to kind of make Carbon public. And I just want to remind folks, how many folks here like have saw the announcement video and have some familiarity? Not everybody, is cool, right? So just as a reminder, Carbon is our experiment in what a successor to C++ might look like. What would be a really compelling successor? They started with our goals for C++, right? Performance, software and language evolution, code that's easy to read and write, right? Safety, testing, fast and scalable development, and of course supporting all of the modern platforms. But we're then going to change this by adding interoperability and migration from existing C++ code, and hopefully the ability to really emphasize language evolution, something that can evolve over time. So that's what we're trying to do with the Carbon experiment. Been running it for 2 years. It's running really well. It's an open source project. You can kind of see when we announced it here 2 years ago, that would be the giant vertical line. Go CppNorth. You all are awesome. Really appreciate that. We've had a huge number of contributions over the last 2 years. 1,750 PRs merged. I think this is actually out of date already. I did this, I got these numbers on Monday. 121 new contributors over the last 2 years. We have a Discord server that's active. We have project milestones, annual roadmaps. Find the link to the slides. These are all links. You can click on them if you want to dig into these kinds of things. So Carbon in 2024 is really focused on implementation. This centers around our tool chain, right? A realistic compiler that you can go and build Carbon code with and actually evaluate it. We're making really fantastic progress on that. Unfortunately, this talk is not about Carbon's tool chain, so I'm not going to get distracted by that and spend the entire hour there. So let's talk about something else. Let's talk about some really weird parts of language design and something fun that happened for me. So let's talk about Variadics first. Everyone here familiar with C++ Variadics? We're going to start with C++. All right, so I'm going to walk you through everything. So we have C++ Variadics. We've got a min function that we're going to call with some parameters. It's going to return us the minimum 1. We've got a normalize function that's going to take some pointers, figure out what the min is and subtract that minimum from all of them, right? Pretty straightforward. But with C++ Variadics, you have to have this like template parameter pack for all of the different types. And then you use all of those different types and the values, and so it's really hard to see what this type is. But when we get down here, we're dereferencing values, and so it's probably a pointer-like thing, maybe. And then we're kind of subtracting, and we use a little trick with the comma operator. And so this just takes advantage of the fact that subtract an assignment, even though it's kind of weird, that's an expression in C++, and we can bundle expressions on one side of a comma operator, and then we can use the fold expressions with the comma operator to expand all of the parameters of the variadic. So this is kind of weird and complicated. Anyone disagree with that? Yeah. So my big question, though, when I get here is like, what on earth does this code mean? You don't have an idea of like what this really means? Like, what is it for this code to be correct? Does anyone here think this code is correct? Some hands, maybe, maybe not. It's kind of hard to tell. So the first thing that a bunch of people, I think, would probably point out is I'm just passing around these parameters by value everywhere, and maybe that's inefficient if they're allocating memory or something. That is true, and that is not what this talk is about, because otherwise we'll spend the entire time talking about values and forwarding references and a bunch of other stuff that I don't want to get into. So just for the purpose of illustration, we're going to keep nice, simple parameter passing for the whole talk. But this isn't actually a correct variadic function. There's something kind of fundamentally flawed about this, and it's a little hard to see. Let's start fixing things. So the first thing I really want to fix is these types. So So you have these t's and the single t over here in min. I don't know about you all, but I really don't trust heterogeneous comparisons, especially like chained heterogeneous comparisons. I have no idea what that means. I think the semantics are incredibly unclear. I don't want that. That's not my goal here. What I actually want is the same type for all of these. And we can almost achieve this with C++. We can say that this requires that t is the same as all of the t's, right? And this is actually all the t's, because when we use t's here, we then use this ampersand and another expansion, and this gets us the same constraint for all of the different t's. So that works. It's really kind of wordy, but it does work. Fortunately, there's an incredibly quirky and bizarre thing where you can just leave off the t's parameter entirely and move same as up here, and it means the same thing, which is magical, but very terse, so we've got that going for us. All right, so now we've said these are all the same type. Do you think this works? Anyone think this is correct? People know about variadics here, right? So if we write a little test case and we pass like a size t parameter A and an size t parameter B and then a 0, just a literal 0, this doesn't compile because that 0 is type int. And we're still going to deduce different types for each of these parameters. And then after we've deduced the exact type of each of these arguments, we're going to say that they have to be the same, and they're not the same, right? So we don't quite want this. It doesn't work the same as a function that has the same type in each parameter because no implicit conversions happen. So we can kind of fake this with std convertible to, which isn't quite the same as an implicit conversion, but okay, maybe it's close enough. And so we can do that. This is at least close. Okay, so min is mostly working now. What about this one? We also don't have any types here, and we'd really like types here. Fortunately, this one's a bit easier. We have pointers here. We don't have to worry about implicit conversions or any of the other fancy stuff. We can just say that these are all double pointers, right? And that's going to make this code a little bit more explicit and clear. I mean, it's in a weird place to say that values are all double star, but whatever, fine. So folks think this is correct now, right? We've got types in this. Like we're getting there? No? Everyone's like, no, you've got a trick up your sleeve. So there's something wrong here with star values. And I genuinely actually find this hard to see. I'm not just like leading you all on. Like I really have trouble seeing why this is wrong. But it is actually fundamentally flawed. So the reason that I find this hard is a little bit weird to me. I've spent a lot of time looking at variadic code, writing variadic code, and it's always been difficult, and I didn't understand why. Especially because I don't have the same problem with templates, right? Let's take a very simple template, just the simpler version of min, left and right, nothing fancy here. We still have this unknown type here, t. We don't know anything about t, but I do know what I do with t, right? I compare it, and I return it. Okay, and I can kind of internalize, okay, that has to actually mean something about what t is. I can even write this down with C++20 that like t has to be copyable because I'm going to return it and totally ordered because I'm going to do comparisons with it, right? And C++ won't enforce these, sadly. That's something I really wish it would. But it does let me say that there's a model here. There's some underlying model that I'm expecting to allow this code to work reliably. All right, and that's really, really nice. That's how I think about template code. I think of it as this generic thing with these generic types that are symbolic and have these properties. But I don't have that model for variadics, and that's actually a real problem for me. And so, despite that, unfortunately, Carbon has to support variadics, right? If C++ has variadics, we want Carbon to succeed at having seamless interop with C++. We've got to add variadics to Carbon. And that's tricky because they can't just be normal variadics like C++. We need them to be generic variadics. One of the big things that Carbon does is it actually does definition and type checking of all of your generic code. And that means when we add variadics to Carbon, we want the same property, right? That we expect the compiler to tell us if we get this variadic wrong, not to have to stare at it. So a colleague of mine, another person on the Carbon team, was working on this, and I was helping out with this. And there were some surprises. First big surprise, almost no languages with definition-checked generics have variadics. Haskell doesn't have variadics. Rust doesn't have variadics. Actually, while we were working on variadics for Carbon, Swift published that they were adding variadics. We had a really great opportunity to sit down with some of the Swift language designers and talked to them about how they did Variadics. They took a very restrictive, simple model that works out really, really nicely. We actually kind of talked through the trade-offs that were involved. They were super helpful. It's like the only other language we know of with definition-checked generics and Variadics. And so this is a really unexplored space, especially in a kind of production-aiming language. And so I want to dig into this and kind of share just a peek what this design looks like, but I do need to make sure everyone here can at least read the Carbon code I've got up on the slide. So we're going to do a super fast crash course. I'm not going to get you all to where you're comfortable writing Carbon. You don't have to know everything. It can be a little head scratching. That's fine. I just want to make sure you all can read the code on the slides and follow along as we go through the story, okay? It's a super fast crash course on a bunch of Carbon code, right? Carbon, we have functions. They start with fn, a little keyword to introduce them. We have parameters. The parameters look like Rust parameters. If you've seen Rust, right, you have the identifier in, and then a colon, and then the type. We use I32 instead of int. This, again, looks a little bit like Rust, just being explicit. We have built-in tuple types. So we can return an I32 and a bool here as a tuple. We have local constants, right? Limit is an integer local constant. We can cast expressions, and so this calls the square root function and then casts that to an I32. We have local variables, nothing too surprising here. We can return tuples as well, so the tuples are also built-in expressions. We can also do destructuring. This is just like a destructuring thing, but we actually use a little bit more rich pattern matching system here. And so this matches the I32 first element of the tuple in the return and binds factor to it, and then matches the bool in the second element, binds has factor to that. Make sense? We also have definition generics in Carbon. And so this is the syntax we use for that. Not angle brackets, but square brackets. I know people are frustrated by that, but just bear with it, right? So we have a t-type parameter to this generic function that we're going to deduce. And we constrain that to support addition. This is the plus operator, is what core.add gives us here. And we use that for both parameters and for the return type, okay? We call print on that generic argument, x, right? And when we do call print on x, we're going to pass x to another parameter of another generic function, arg, right? Arg's type here is p, which is also deduced, right? And p is constrained to be printable. It's a print function. You've got to be able to print the type that you handed. Unfortunately, right, this doesn't compile because t wasn't printable, right? T only supported operator plus, didn't support printing. And so we get a compile error that says, no, you can't print something just because you have an operator plus. You need this to be printable, okay? And we don't have to call generic sum to get this error. We get this error right away. Make some sense? Okay. So I told you, really fast crash course. So how do we then build a variadic system on top of this? The first layer we're going to need is syntax for variadics. So let's go through just kind of the syntax and the structure of variadics in Carbon. Right, so we have a couple of variadic functions here. And there are two main things that you see with variadics. One is you want to introduce a variadic pack, right? And so you do that in an argument list or in a variable declaration. Right, so here we're introducing two variadic packs of params. You can see these are I64 variadic packs. They actually have a fixed type. We also can expand these packs inside the body of functions to do things with them, right? And so this is a statement expansion. We also have expression expansions. So we dig in a little bit deeper here. We have each param, and whenever we're declaring a pack of things, because packs change the structure of the code itself, they need to be really, really visible when you're reading the code. It can be really confusing if you can't see that there's something that turns this code from kind of a normal set of code into this variadic thing that's expanded. And so we require every pack name to have a keyword prefix of each, okay? This also really helps with naming because packs are weird. They are both multiple and singular, right? You obviously have multiple of them, but you use them in singular ways. And so it's really hard to pick a single naming convention. Using the each keyword really helps you here because it's like, oh, obviously I'm going to name it singular, but I have a reminder that there's more of them in theory, right? And full credit to Swift for this idea. It's a really, really fantastic idea. And we do that even when we're expanding them, right? It's always each param here. When we look at a statement expansion, you start with 3 dots to expand a statement, and we can't expand an entire statement here. Plus equals in Carbon is a statement, right? Ends in a semicolon. And this just pastes out that statement for each of the params, okay? And we can do an expanded expression very similar to C++, where we're going to repeat this expression separated by commas, right? And each of these is going to be each param times each param, right? We're just squaring each of our parameters. Following so far? Everybody happy with this? Great. So now we have syntax. What does normalize look like? So we have this min function. We're going to have a deduced t type. We only need one type now, but we can actually deduce it. We can even say that it's ordered and copyable. We can like add some of these constraints to it. We still have the first one peeled off because you can't really compute minimum of 0 things. That doesn't make any sense. We need to return an element of this list, so we peel one of these off. And then we have each of the next ones in the pack at the end, right? We know we get to return t, really nice. In normalize, we get to have a pack of these argument, like each of the values we want to normalize. We know that they're both pointers, right? F64 is our double type, same difference though. We expand it in the expression. Our expansion starts at the beginning. We find that a little bit easier to read. Dereference each of the value pointers to go to min. Then we expand a statement to actually subtract. Dereference each of the value pointers in order to subtract and assign to it. Do the subtraction of min. Make sense? Pretty straightforward. I find this a little bit easier to read. We get to not have comma, operator, fold expression stuff. I'm really happy about that. And just to be super clear, right, we haven't changed that much. Like there's a perfect correspondence here, right? So we have the t part. There's the extra stuff that we don't need in C++, right? We have first. We have the pack, right? We have the double type. It's in maybe a less surprising position, but we have it in both, right? We have the extra stuff in C++. Then we have our value. We have our min. Do our subtraction. There's nothing like earth-shattering here. Like these are designed to be really easy to move between. Okay, so that's nice and all. But the whole point was to type check something, right? So what's the model? How do we actually type check this? That's the interesting bit. So let's get into type checking packs and pack expansions. And to kind of explain how the type checking works, I'm just going to use local packs just to do a little really easy. And I'm also going to use a bunch of kind of pseudo syntax inside of comments here just to illustrate what's going on in the type checker. So we have a big tuple here with a pack expansion in the middle. And we want to know what the types are. Well, the first and the last one are really easy. We have an I32 and an F32. Like that's pretty straightforward. It's written in the code, right? No big deal. The real question is, what is this one, right? And so here we want, some number of repetitions, and we use this kind of Unicode double bar thing to mean the arity of each param. That many repetitions of I64s, right? That's the type of this inner piece of this tuple. We can actually, we build a little pseudo syntax for writing this, where we say we have I64, but not one of them. We have each param of them, right? The size of each param, right? And so now we can stitch all this together, and we have kind of a type here, right? We have I32, then a sequence of I64s, and then an F32, right? That's the type of this tuple expression. Make sense? Right? And this is not, this is not Carbon syntax, right? Like this is just kind of notation. We're using Unicode because this is not code that you're ever going to write or see. All right. And this is also the type of X. X is the exact same type of its initializer here, right? It's a pack. But even though it's a pack, we retain its structure, right? We understand how the different types are segmented and repeated in this. We can actually model all of this symbolically. And so now we can ask, what's the type of 2 times each X, right? And so this is going to be, whatever 2 the integer literal is times each X. And the way we do that is we just loop over each segment of the type, right? So first we have 2 times an I32. That's an I32, no big deal. Then we're going to have 2 times an I64, right, for some number of repetitions. That's an I64 for that number of repetitions. And then we have 2 times an F32, right? That's F32. And that's our type. right? And so just looping over them is all you need to figure out what the type is here. Let's make it a little bit more complicated. Let's have two different packs, right? We're gonna have A and B. A starts with an I32, followed by a sequence of I64s. B is an F64, followed by a sequence of I64s, okay? So now we wanna look at what's the type of each A times each B, right? Well, we take I32 times F64, right? And the type of that multiplication is gonna be F64, right? And then we have I64 times I64. The result of that is I64, and we repeat it by each param number of times. It's really easy, right? What was hard about having a type system here? So this part really is easy. There's not like a secret here. We think this is really straightforward. You have, pack and tuple types. It's just a sequence of type segments, right? And each segment has a type and an arity, right? Let's just represent repetition and arity explicitly, but generically and symbolically. Like, we don't have any numbers in these arities in a bunch of cases. And then inside of a pack expansion, all of the expressions and patterns, they're gonna have pack types, right? With this structure and this sequence of segments. And they all have to have the same shape. Because they all have to have the same shape, we can just loop over the segments in order to do type checking. Make sense? So let's extend this to pattern matching and specifically function calls in Carbon. So we've got some variadic functions now. And I'm gonna put all of the type state over on the left side here in our pseudo syntax, but I've left like ASCII art so that you can see what it is we're tracking the kind of type state for. What we really want to type check here is int sum, like this call to int sum with an expansion of each x, right? That's the interesting thing for us to type check. And so we know that this is a sequence of I32, right? And we can look at what the function we're calling is, and it takes a sequence of I64s, right? These match up, so we can say like, well, I32 promotes to I64, no problem, so that'll type check just fine. Then we have the arity, and the arity of the call is each x's arity, okay? And then we look at the parameters, and it has a deduced arity of each param, right? And when you have arities and parameters, they're deduced. When you have arities and expressions, they're symbolic. But that means we can just deduce the arity of each param to be equal to each x, and we're done, right? This type checks. Sorry, I went too fast. So this type checks. All right, so let's look at a more interesting case. Let's look at a case where we have multiple parameters all going into a single pack, right? So now our int sum is a little bit more complicated, right? We still have the each next down here, but we added a first parameter, or argument, sorry. But that's okay, right? Because all these are going into the same pack on the parameter side, we loop over the arguments. We have an I32 first with an arity of 1, then we have an I32 with the arity of each next. We loop over all of those. We make sure each one of those actually can be passed to the parameter type I64, right? And I32 promotes, and so that's fine. That's trivial. It's a little bit more tricky to actually figure out the arity, though, because now we have more than one thing. That's okay. We know that each param is a deduced arity. And while we don't know what each next is, we know it's a symbolic arity, and we know we can add 1 to it. And so we need to deduce each param's arity to be 1 plus the arity of each next. That's something we can do symbolically. That's fine. And so this type checks. Make sense? And now we're back to our min example and our normalized example. So how does this work for our example? Well, we've got our type state here. Now we have one pack being expanded, but 2 parameters that we have to go into. Right? So for the types, this actually works out okay. Right? We have one argument type, F64. We have multiple parameter types here that we need to deduce, but they're all the same type. Right? And so that's easy. We can deduce T to F64, and that's going to satisfy all of the type constraints we have here. Then we look at the arity, right? Well, we know that we have a symbolic each value arity, that's the argument side, and we need to deduce each next. So what does this deduction look like? Let's just write out the equation, right? We do 1 plus each next arity needs to be each value's arity. And we can subtract 1 from both sides, right? And we get each next arity, right? What we're deducing needs to be equal to the each value arity minus 1. But now we've got a problem. You can't subtract from a symbolic value. It might be 0, right? So this doesn't make any sense. right? And this is a compile error. So this is our model. This is the crux of the model. Once we have these type segments with symbolic arities, we can actually build a type system that goes and discovers, no, you actually have a hole in your entire variadic here. If you call normalize with no parameters, normalize seems fine with that on its signature, but we actually can't implement the body of it because you can't call min with no parameters, right? And we can actually model this symbolically, and so Carbon's going to give you an error message when you define normalize this way. You're not going to have to wait to call it. You don't have to write the right unit test to catch this, right? So this, for me, was just revelatory. This was super exciting. It's like, now I know there is a model, right? And I have it in my head, and now I can use it, right? I even know how to fix things, right? So if we want to fix this, well, we need an extra argument to normalize, right? And so if I have this extra argument here, I can even pack it back in with a local pack of arg. That's fine. That doesn't matter. Because now I understand the structure. Right? I know, sure, I have f64. We know that this is fine. But now I have each value plus 1. I know I added another piece to the arity here of each arg. And that means my equations are 1 plus each next has to be equal to each value plus 1. I can subtract 1 from both sides, no problem at all, right? And I actually can deduce the arity here. Right? This tells me what the difference is between these two versions of normalizing. Why one of them is reliable, it's durable, it'll always work no matter how many arguments you give it, the other one doesn't. All right, questions about this? What about some harder cases? Like I've kind of like, you may feel like, have you just like cherry picked this like extremely easy case for us? Yes, I have. So there are some much harder cases like zip, which I am not going to explain. So the fun thing about zip here is that zip wants to peel off the first argument as well because we don't want to zip a bunch of empty tuples together. That doesn't make any sense. We don't even know how many of them to produce. So we peel off one to make sure we have the right arity in the definition of zip, right? But you might call zip and expand an argument in the first argument. And then you have a pack in the second part of zip, but you've put your explicit single argument in the second part of the call. This is actually really hard to type check. But I don't have time to go through that. If you want to, Jeff Romer, the person who's actually been driving the Variadics design, gave a great talk about this at C++ Now. I don't think the video's online yet, but it is going to be posted online. Check it out. He goes all the way through this. There's a whole bunch of surprising things that go wrong that then we have to fix. It's a great talk. My real point is that we actually can use a type system model to think about variadics, right? That, I think, just the fact that this exists and is available is super exciting. And in some ways, even more fun for me is that like designing the feature for Carbon is actually how we came up with a really nice articulation of this model, right? This forced us to say how variadics work, right? And not just for Carbon, that's the other fun part, right? So we have both of these. Remember how close these corresponded. Now that we have a model for the Carbon side that says why we have to reject this expansion of each value in min, that's the same reason why the C++ side is wrong, right? We can actually use the way we're thinking about variadics and Carbon to think more deeply about our C++ code, to build better APIs in C++, to design variadics that are going to be durable and much more reliable, right? Like that's the nice thing about having these languages so close together. All right, so cool. Variadics and Carbon that kind of reflect how C++ works. This was my first cool observation. Of course, just like one-off observation, that's not interesting. The real question is, does this happen for anything else? This is the only time where this comes up. And it turns out this happens all the time. Okay, I can probably give this talk 3 more times and never repeat a story, right? Which is really, really cool. We keep seeing this come up. So let's talk about one more really fun thing. Binding members. And now I'm going to pull a little bit of a JF here and just ask you, like, what do folks think x.y means? Any thoughts? Go ahead. I'm sorry? Is y a member of x? Sure. But what does it mean? I didn't do anything with it. Like, am I going to call it? Am I going to take its address? Am I going to modify? What? We don't have a model for what x.y means before I do something with it. And it can mean a bunch of different things in C++, right? We've got methods, we've got static functions, we've got fields, right? And Carbon has the same problem, just to be clear, right? Carbon has methods, and it has static functions, and it has fields. It's all the same. There's actually more stuff in C++ because there's another way of writing something like x.y. You can also write, you know, a colon in between things. C::: method, static and field. And like these are really mysterious. I think I can fill in the question marks for the middle one, but not for the other two. And the only reason I can fill in the question marks for the middle one is because of like a bunch of weird implicit stuff that like no one really likes to think about. And Carbon also is gonna have this problem. We even make it a little bit more obvious. We still call this with dots. So this is C.method, C.static, C.field. And these are all different, right? And so we really needed a model in Carbon for what this meant. What it meant to take a member and attach it to something on the left-hand side of a dot. And we wanted that to be kind of a principled, really robust model that we can use to think about how Carbon works as a language. Especially because we need to support some really funky stuff from C++. Because you can do this with C++. You can take the address of a field, no object in sight, right? And you're gonna assign it to this pointer to a member, pointer to a non-static data member, there we'll go, which is a thing that is not a pointer. And this address of does not take the address of anything because there isn't anything to take the address of. It's very confusing what this is to me. And then you can use it. There's a special .star thing you can do in C++ to use a pointer to a non-static data member with an object of the right type to access that data member or field, right? Okay, so that's cool. And you can do this with methods, which is fun, right? And you get this thing, which is a pointer to a member function that returns int. And I have a typo somewhere. This should be a const here. Anyways. And you can do the .star thing with this, but what you get is now different because what you get is not something you can do anything with except call. And I mean, literally, you can't do anything with x.star PMF except call it. There was a GCC extension for a long time that let you do something else with it. Don't use that. It does not work reliably, right? But like, that's kind of weird, but okay. So then there's inheritance. Inheritance actually makes this incredibly more complex. I'm not going to talk about how inheritance works with this today. We don't have enough hours. I don't know that we have enough days. Okay, so how do we actually support all of this stuff in Carbon, and does that give us a model for thinking about C++, right? Let's see how we do this. Now, unfortunately, the crash course in Carbon has to continue in order to get into this, and I've got to get a little bit deep into Carbon internals. So hang on, we're going to do this. It's going to be okay. All right. So the first big fundamental part of Carbon you need to understand here are interfaces, right? Interfaces in Carbon are what they say on the tin. They are the kind of most abstract way of describing an interface of a type, right? It's some interface that some type might implement. You can think of these like C++ OX concepts or Rust traits, Swift protocols, I don't know. There are other languages probably have other names for them, right? But we call these interfaces. In Carbon, it seems like a really self-descriptive term. We have associated types. It's just like if you have stit vector, right? Then inside of stit vector, there's a value type, right? If you have an iterator type in C++, you might have a value type for it. This is the same thing. This is a result type for this interface. You can say that this interface has methods, right? And this method has a return type that's one of its associated types. And this is just a common core pattern, is that you have a bunch of associated types in your interface, and then some functions or signatures built using those types, right? Now, if you have a type C and this interface, you can implement C as that interface, right? This says basically, if you use C with this interface, here's an implementation you should use, right? And in that implementation, you have to like fill out all of the associated types. So we have to say that result here is going to be an I32. You have to define what method you actually want to use here. We now know it's going to return I32 because we're in the definition and we set that, and provide a method body, right? And now when you take some variable of type C, you're going to be able to take that variable and use a special member syntax, right? Open paren I.method, close paren, is going to actually call this interface method on the object X, right? Doesn't care what X's API, what C's types is, like what the API is there, that's fine. It's just gonna go and look at how does C implement I want that method, right? This is basically the same as taking C as I, right? Remember, as is a cast for us, turning C into an I and calling method on it, right? There's also other shorthand syntax, doesn't matter. And this is also what powers our generic system, right? So if you have a generic, you can say you take some type T, right? You're gonna have T implement I, and because we put I in this kind of type position, that's actually gonna give you I's API anytime you interact with T, right? And if you take a parameter of type T, it's gonna give you that API on the parameter as well. And so now we can say T.result is the return type of this generic. We can return Y.method. We can type check this definition because we know from the interface that method has to return the associated type result, right? We don't need to know what type we're calling this with to prove that those will type check. Then when we come down and call it with a particular X, right, with a specific type, we say like, oh, okay, T is now equal to C here, but we're still gonna use the I interface, right? So this still calls the method we have defined here. Make sense? All right, interfaces are incredibly foundational in Carbon. We build literally everything in the language on top of them, and for a reason. This is a single extension point that we can build on, and it ensures everything we build is available inside of generic code, right? If we didn't build on top of interfaces, we would end up with something that worked outside of a generic, but didn't work inside, and we didn't have a way to communicate that language construct into generics. And so it's super important that the thing we use to build generics is also the thing we use for all of the other extension points and customization points throughout the language, right? So we keep following this pattern for a reason here. And so, since we build everything in Carbon off of interfaces, and we're trying to figure out what a bound member is, we're gonna build member binding on top of interfaces, naturally, right? And so we've got an interface here, and the interface for doing member binding is called bind to value, okay? But it's not just an interface, it's a little bit fancier. This is actually a generic interface, because it's parameterized with a specific type, okay? And so this is saying I bind to value an object with some typed object. And you have a result type. Told you this was a common pattern, right? Then you have this op function. We have a whole bunch of interfaces, especially doing stuff like this in the language, where there's not a meaningful second name, right? We've already said what this is. We just need the function that provides that behavior, and we, by convention, just call that function op. And this is gonna take some object of the type that was our parameter, right, some X, and it's gonna produce that result type, right? And this is basically how you can do member binding. But it's a little bit weird to see how we get members all the way into this interface, and so bear with me, I'm gonna try and stitch it together for you. So if we start off with X, which has a type T, and we have some member expression. That weird syntax with parentheses uses a member expression, okay, rather than a member name. And what we do when you use the syntax is we flip it around, and you're gonna see me with this squiggly arrow. Again, Unicode, this is not real Carbon code, right? But we're gonna use kind of a semantic rewrite from one piece of Carbon code into what that means in practice. So we're gonna rewrite this into the member expression and actually accessing this bind to value, but for T, and we know it's T because X's type is T, right? We're gonna call the op function within that interface, and we're gonna hand it X, right? And so it's actually the member expression that does the binding onto an object X. Follow me so far? I know it's all right, I'm gonna stitch it all together, don't worry. Okay, so now we need to actually get one of these member expressions for a member. How do we do that? Just imagine we have a type C with a field. We're gonna synthesize a type for every named member in a class, right? Type of C field, right? And we're gonna also synthesize some constant, right, of that type that represents this field. And we're gonna provide an implementation for that type of bind to value of C, right? And what's the result type of binding a field? Well, the type of the field, right? That one's pretty straightforward, I32. And what does the op do? Well, it takes the object, right? It takes the C object. We know it's going to return I32 now. And then we have some compiler magic to like reach inside the bytes of the object and be like, okay, at this, we got X, at this offset, we're going to go find an I32 and return it to you, right? This basically implements fields access, right? I know it seems like a lot of machinery for field access, but like, stick with me. So let's squeeze all that machinery up into the top half of the slide, and let's look at how we use it. We get our X, right, of type C. We have X dot field. We want to figure out what does this mean. This is a name. This is not an expression, right? So how do we actually implement this member access? Right, well, first we turn it into an expression by going and finding C dot field. And this is actually an expression. This says, like, I want C dot field. And what does that expression produce? Well, it produces that constant we synthesized, right? We're going to take that constant, move it to the left, right? Reach into the bind value interface for C. Find that op function and pass it X, right? And if we inline the body of that function, right, what we're going to get is this compiler intrinsic that implements field access of X at an offset against this field. Okay? And so this gets us from this tells us how X dot Y, when Y happens to be a field name, gets to the actual value of the field. A lot of machinery, right? What does this actually let us do? How is this an improvement? Well, now we can do some really cool stuff with this. For example, we can define a function f. We can take a type. I can also take another type that implements bind to value for the first type, okay? And this lets us take an object of some type and some expression that is a bound member of that type, all right? And we know that's what this does. We even know what the type of that applying that bound member will be. It'll be u.result, right? And we can take that object and use our special dot paren syntax to apply the bound member to the object and get the result, right? So this gives us pointer to members. But even better, it does it without it being a pointer, right? This is actually explaining like, no. We're encapsulating whatever we need to access that field in a bound member into this bound member value and passing it along and accessing a field, all right? And this is called f(x) c.field. Make sense? Okay? Okay, so yeah, great, we've implemented pointers to members with a lot of machinery. C++ has a lot of machinery itself, but like that's not an improvement. If we really want this to be good, we need this to generalize, okay? We need to generalize to other kinds of members. And we can, but it's tricky. And we're going to need some more infrastructure in Carbon to do that, okay? So I've got to introduce a couple more infrastructures, pieces of Carbon. The first one are adapters, all right? So Carbon allows you to define a class, let's say A, and say this type adapts this other type C, okay? That means it has the exact same representation. And in fact, you can just cast back and forth between these types, right? If you have some X of type C, right, you can say X as A. This doesn't create a copy. This just says like, nope, I've switched the type of X over to A, right? We can cast it back to C. Again, no copies or anything. This just changes the type, right? This is basically the new type idiom from Rust. You can also do this with actually the new type keyword in Haskell, right? This lets us construct new types that can refer to the same objects. This is an incredibly powerful tool to have in your language. It's awesome what you can do with it. One thing you can do with it is you can provide new interface implementations that are different for the same object. And so, for example, if you remember, we implemented my I interface for C. I can implement A as I as well. And it can be different. I'm going to say that for A, the result is going to be F32, a floating point. And I can implement my method that returns an F32. And this is a different method from the C as I method. And if I come down and I use Y, right, which is type A above, I can call I.method, same syntax I used for X, but this is going to get the method here that returns an F32. It's not going to get the one for C. So this lets us have different implementations for the same interface for the same object by changing that object's type, right? I know it seems kind of obscure. Trust me, we're going to use that. We've got to use it in conjunction with something else, all right? And the other thing is, how do we model function calls in Carbon? Now, we could give a whole talk about how we model function calls. I'm going to distill it down as much as I can to this one interface call. We're going to pretend that there are no arguments to function calls for the rest of the talk, okay? It's just magically all of the arguments are going to go away. And that just for the talk, okay? So we have this kind of basic call interface, right? All we have is a return type because we don't have arguments. So your op takes no arguments, produces the return type. No big deal. And this means when we're defining functions in Carbon, we're not actually defining something new when we write this. We're actually just writing some syntactic sugar. This turns into a type that we synthesize and an implementation for that type of the call interface, all right? And we say that the result is going to be whatever return type we wrote in our function definition. We have an op method, right? We put our definition inside that op, right? And now we can build a constant f with the type that we synthesized, and that f is callable, right? And this is actually how function calls work in Carbon. And this is kind of cool on its own if you think about it, because we've just unified lambdas and functions like entirely into like one core construct, which is pretty nice, all right? There's one model for all of that stuff. Well, how are we going to use it for members? We're going to start with a static member function. It's a little bit simpler than a method. And at first, this works exactly the same as a field. There's no interesting difference, right? We have a static member function. We build a type for it, right? We build a constant of that type. But we're also going to synthesize this binding C static class. There's a special class that adapts C. And we do this for members that are functions, right? Because they don't have, they're not storage. They don't have a special storage inside the body of your type. So we adapt C to build this. And when we implement the type of our constant for bind to value, we're going to have the result be this special binding C static type that adapts our object. That at least lets us return it, right? Our op takes in an X, type C. It has to return this binding thing, but we can do that because of adapters. We just convert X into this binding object. Pretty straightforward. Okay, so squeezing all of that up to the top, let's see how we use it, right? We have x.static. We're going to rewrite that to x dot, and in parentheses, the C static, which is just a constant here, right? We're going to move that constant to the left-hand side. We're going to apply this whole bind value machinery and the op function within it and call that with x. With one problem, we're defining how you call functions and we're calling a function. That's not good, right? We could recurse endlessly here. And so instead of actually doing this line and what it does, we of course have to have some compiler intrinsic that doesn't recurse back through how you call member functions, right? So we just have a compiler intrinsic to bottom out recursion whenever we reach into the special bind to value interface, right? This makes bind to value truly special. Yes? I'll repeat.
This is applicable to the field case as well, but when you rewrite an x.y expression like on this slide, x.static into something that also uses dot, how do you tell that in the result that dot is not subject to the same type of expansion rule?
So note the parens. These are all dot parens. I never use dot without parens after I start the rewriting.
Okay.
And so dot parens is different. And that's how we tell the difference. Okay. Until we get to this bind to value C op, when we can't with dot parens alone, and we need some compiler intrinsic to do that for us. Yeah. Okay, so we have a compiler intrinsic. It does our bind value op call for us magically, right? And then we get the body of that. If we just inline that, we can see we have X as binding C static. Okay, almost there, I promise. So now we need some way of calling that. Well, we have a type binding C static, and we can implement for binding C static the call interface, right? We set the result to the return type of that static function I32, right? We have the op. We go in, and we need some way inside of our op to call the c.static, but obviously we don't want to, again, recurse back through this. So we'll have a compiler intrinsic that calls the function here. And this isn't like, c.static that we usually write. This is all pseudo syntax. This is the function definition we wrote up with c.static, right? And of course, we don't have any arguments because we're not handling arguments now. We're just handling the basic calls. Okay, so now we can finish our rewrite. We started saying that x.static turns into this x as binding c.static. Now we need to rewrite the call part of it. That turns into call.op. But again, we're implementing calls. We can't actually do that. So we need another intrinsic to call call.op with x as binding c.static and the parens. And that inlines the body, which is this function call to the c.static definition with no arguments. Right, so this gives us static functions. Static functions, though, aren't the interesting thing. The really interesting thing is that we can take the exact same thing and we can do it for methods, okay? So let's try methods really quick. We got this. All right, so we got a method, type of the method, the constant for that method. We're gonna have a binding type that we introduce that adapts our type. Right, then we're going to implement type of C method to bind to value C, the results of the binding. All of this is exactly the same as with statics, and we like that. Right? We want this to be the same, right? Because that gives us some general model between static functions and methods. Right? And then the rewrites. The rewrites are also all the same. Right? You take your method, go to c.method, the constant, move the constant to the left, apply bind to value op using an intrinsic, so that we don't kind of recurse indefinitely, and we get to x as binding C method. Right? With me? The interesting part is buried here, and that's good because it means we have more and more generality. So when we take our binding C method, we go to implement that as call. The return type works the same, right? Methods have return types just like any other callable thing. So all of this doesn't look like a method until we get to the body of it. Only inside the definition do things change. And that's because somehow we need to go back to having our x. We need to find our object of type C. And we can because we're an adapter. Our self inside the adapter can be converted to C because that's what adapters let you do. And that means we can get it back to C and we can call a method on it. Of course, we can't call it literally because we need a compiler intrinsic to do this. We're implementing method calls. But we then say, like, wherever your method body definition is, you take self passed to C and no arguments, and that's how you call a method, right? And so now our method rewrite is the same as static, right? We turn it into our binding. And when we go to our call, this rewrite's also the same. Call turns into call up doesn't work without a compiler intrinsic. We pass in x as binding C method, no arguments. We get the compiler intrinsic for the method call, right? Only the last thing is different, and you can see x show right back up here, right? And so this unifies all of the stuff we're doing for static functions and for methods, okay? They're all just callable objects with an adapter, right? Every single thing you can call in Carbon is just a callable object. So why do we want all that machinery? There's a lot of machinery. I know I just like opened up the fire hydrant. I'm sorry. There's a lot of machinery here. But it tells us what x.y really is, right? It tells us what this does, right? This applies a binding, right, that's customizable depending on the type of y, right? And specifically, a constant we look up for y. And we can do stuff with that. For example, you can write this make call generic that takes a t that can be called where result is I32. And this will take any callable that can be called where it returns I32. Right? All it does is it takes that, it returns I32 itself, and it calls it. And we can type check this before we ever see a call to it because it's a definition checked generic. And now we know we can just take this generic function, we can pass x.static, we can pass x.method, and when we do pass x.method, right, it's going to actually pass the state that it needs so that the definition of our method can actually get a field and return it for us. We can even pass a field that happens to be a lambda. It doesn't matter because as long as whatever we pass here implements call, this works. Right? We have a very nicely decomposable and generic model. We don't even have to talk about pointer to members or anything like that in order to pass these things around. We can actually get something that's more common and more general. Right? And so this, to me, is really exciting. We have this completely general model for binding a member to an object. And we actually go a lot further. We handle things like binding to types. We handle different value categories, everything you might imagine. Like I've simplified it for the presentation, but it really does give us this nice general model for binding a member to an object. But what on earth does that have to do with C++? Also, I apologize. I made a mistake in my slides, and I swapped Carbon and C++ sides here. I'm very sorry for the confusion on that one. Carbon's on the right-hand side this time. So the really nice thing for me is that this is actually a model for exactly what we have in C++. So let's work through it. We have an object that we're going to pass to some getField function, right? And we can pass that in both languages. And we're going to pass in a bound field, right, or a pointer to member in C++. Now in Carbon, we do give that a type so that we can actually manipulate it in an interesting way. We don't really have an obvious type in the same place in C++. But we say it's going to be a bind to value operation. In fact, we have that in C++. That's what : means in C++. You can't really use it on its own, but that's actually what it means. Right? We know that it binds to value for a specific type, C. C++ also shows you that. We know that the result of that binding is a specific type, an i32 or an int in C++. We also model that here. Right? We can then take that object. We have a special syntax for doing an expression-based member access, and we can pass it in. Right? Fully generalizes all of the stuff that C++ supports. Right? You can call this with x, and however you get to the field constant, right? And it works just fine. Call method, same thing. We have an object, right? We have a bound method or a pointer to a member function in C++. Right? You have T in Carbon because we actually give it a type to model things. But then things start to be the same again. Bind to value exists in both. That's : star, right? The C also in both. We have a thing that's a little bit different here. We actually model the Carbon transitions to a general callable object here, which doesn't happen in C++. But the rest of it's the same. We model that both can be called, right? They both return a particular type. And so we can write the object, we can apply our special member access, get the bound method, and then we can call it, right? So we can model everything you can do in C++ in Carbon, right? You can write this call method with x and that method. But we can do more than that. This is a more general construct in Carbon because we can also take the exact same code and call it with a static member function. Because we actually have a generalized model for what bound members are here. We could even call this with a lambda. It would work just as well, right? And so that, for me, is the really, really nice thing. We actually have generalized this. We've made it all fit together, right? And so for me, like, this models all of the aspects of C++, but then it assembles them into this like larger generalized design. And to be honest, I did not expect designing things or helping design things with Carbon to really teach me that these C++ features fit into a larger whole, right? That was not at all obvious and a big surprise for me. But it did, right? And I now feel like I understand what feature pointers to members are trying to be in C++. I can even imagine how to extend that feature in C++ in a way that would be cohesive and fit together because we actually have a model for it in Carbon. I think that's really, really fun. And so I had a lot of fun doing this with the community. And to be fair, like you have to enjoy this kind of very deep language design topic. If you do, though, right, if you really enjoy this kind of language design topic, I really encourage you to try it out. It's so much fun. Right now, most of Carbon's focus is on implementing a tool chain, so we're not doing a lot of design. But every now and then we stumble across a corner, they're like, we need a design to implement the next part of the tool chain, and we have to pick this stuff up. And they tend to look somewhat weird and corner casey like this. But you can follow along, and you can even participate if you want. And you're going to learn a lot about Carbon, but you're also going to learn a lot about C++. We try to make this process really, really fun and joyful and interesting. We actually have a real blast doing all of the language design stuff in Carbon. You may have done other language design stuff that was maybe less fun and exciting. We try to change that in Carbon as much as we can. That said, if Carbon is not your cup of tea, that is totally fine. I understand I am perfectly biased here. Doesn't need to be Carbon. It doesn't even need to be C++, right? Design your own mini language or a complete language, right? Build a mini language extension and find a way to use kind of designing these systems and designing these wholes to understand programming languages in general better, right? That's really my only suggestion. And with that, thank you very much. I'm sorry I went a little over, but I'm happy to stick around and answer questions. Let's get a mic, though. Let's get a mic.
Going back to the Variadics part of the talk, I'm curious, do you think there is room to write a C++ clang tidy check or some such?
C++, which
clang
check?
tidy check or some sort of static analysis check that takes a C++ variadic function, tries to model it as a carbon function and apply the carbon rules to it, and point out cases where you're trying to call that min from normalize.
That's a good idea. We should totally do that. Well, someone should do that. I don't know. But yes, I think there's room. It'll be tricky, I think. C++ will probably make it tricky. But particularly if you're OK like giving up when you hit a tricky case, probably. Seems really cool. Other questions? I know everyone's hungry. They want food. All right, if you do have more questions, please feel free to find me. And thank you. It was really great giving this talk here.